Hello and welcome to week 8 in artificial intelligence. This week we're going to talk about making decisions, which is in chapters 16 and 17. Chapter 16 is around making simple decisions, chapter 17 about making complex decisions. Probably going to be a certain amount of overlap. Moving into the assignments, I attempt to always kind of anchor us where we are in this progress. We're into week 8. So you need to be working and submitting your decisions paper of how do you make decisions. And I would recommend you don't procrastinate on that topic. And we'll talk a little bit about it here right now. So research AI related decision making approaches. You want to start with chapter 16 and 17 in this text. Describe the approaches to making decisions in AI. Define all the key terms. So if there's a word that's in there it's central to it, describe it in your own words. Making sure that if you include some sort of a citation, unless it's something you're intimately familiar with and can describe it based upon an example. Research 2 implementations of decision enabling AI software. So things that enable things like decision networks, trees, linear programming, etc. Something that helps people make intelligent decisions, leveraging some concept that's related to the material we'll talk about today that's in the chapters 16 and 17. Describe and compare the implementations. So compare, contrast them is basically what I'm telling you to do here. So how are they alike? How are they different? You might even go so far as to make a recommendation depending upon a domain, up to you. Cite at least 4 scholarly sources and utilize APA 7th edition. Anticipate that your word count will be 1,500 or 2,500 words. It's really pretty open-ended. The point of that is 1,500 words is telling you, I don't expect a page and a half. I expect you to spend some thought on this. It'll be double spaced, so let's keep that in mind, but still um, spend some effort, right? The rubric that'll be used to grade the research paper. As always, you want to shoot for that excellent column. It all starts with a strong thesis or topic sentence, and then you want to basically have a list of subtopics that are going to be used to reinforce and to support that thesis statement. So you need a specific thesis statement, and the thesis statement for this is likely going to be that decision making software is an important part of any business situation, or pick your domain. And as such, you're going to explore 2 offerings or implementations of artificially intelligent enabled decision making software. And then you're going to basically you're going to discuss each of the software packages in turn, and then you'll compare and contrast them, and you'll close with a conclusion. And speaking of your conclusion is going to restate that same thesis statement along with describe how your subtopics reinforced that thesis statement and that you actually did what you said you were going to do in the introduction. Remember that introduction doesn't have a heading. It is the first thing after the title on the first page of content. Don't include an abstract. I don't need to see that. Do make sure you utilize headings. They help organize your paper and also helps you on your focus and sequencing grade. Do make sure that you support anything that you introduce as a claim or evidence with some sort of a peer-reviewed research mechanism. So journal article or a book, maybe a conference proceeding. Um, Make sure that, again, you have a conclusion that reinforces what you just said. Make sure that you have reasonable spelling and grammar, punctuation, and so on. Try to get fairly close on APA. I'm not going to beat you up too terribly bad on that, but at least make the effort and use an APA template. And then make sure that your references are reasonably well written. Do make sure that your citations and references also line up. So don't have a reference without citations, don't have citations that don't have a reference. For your week 8 discussion, choose a topic from the reading and talk about it, and give an example of a real world sort of implementation or something you may have seen or read about. Again, useful resources for this course is the Berkeley website, mainly because the authors are at Berkeley. Moving into making simple decisions. And we're going to talk at first about combining beliefs and desire under uncertainty. So to do that, we need to talk a little bit about utility. So what is utility? And the idea here is that you want some sort of calculation, and I believe we talked about utility in the past, but it's a way of calculating what is something worth, and you should you'll probably end up with an average utility, not necessarily min max, but average. And part of that is you're not necessarily in a zero sum sort of situation, right? Um, the the world is not necessarily truly competitive all the time, and you want to maximize your expected utility, and typically speaking an agent maximizes its expected utility given its knowledge, so it's going to do what it can for its own good. That's also kind of a principle of most game theory, is that you're going to do something as an actor in a game or a player in a game. You're going to do something that is to your best benefit, or at least your perceived perception that it's going to be your best benefit. So you may ask some of those questions of where do you get utility and so on. And it comes down, you calculate it, right? So we move into the basis of utility theory, uh, what utility to use. And there's various types of utility, min-max reasoning, which we talked about before in games. Um, and if you go large enough on the tree, the terminal doesn't necessarily matter as much. It's how you get there. Um, And when you're talking about utility, um, it's sometimes it can be a plus or minus in a game. Sometimes it's much more complex about it's how well you reached your goal. How good did you do? If you won or lost, if you scored more points than the competition did, if there are points involved, if you made more money or not, if you're talking about automated trading. Um, and you basically pick your utility and it's going to drive what happens is the concept. um, the trouble you have is with utility, you also have this concept of uncertainty. So you've got something there that's the safe bet, right? Of if you get a single cone of ice cream, probably not going to drop it. Could happen, but not likely. You get two scoops of ice cream, you could lose both scoops, right? It can happen. Higher probability of that is kind of the part of this to consider, is that we are talking about uncertainty. So whenever you're calculating um, utility and utility functions, you're going to consider that. You're going to consider kind of a combination of the probability of something occurring and how good it is if it does occur. It's a basic concept that you're going to combine those two things together. You have, in this case, a prize, and then you got if something is a lottery, you got the probability of winning or not winning, and the probability of winning is p, and the probability of not winning is 1 minus p, assuming it's fair. Um, and rationality is whenever you start doing things that make sense, and it's kind of a redundant way of stating it, but you do something that is in the interest of the thing that is doing it, with a reasonable expectation of success. So you should definitely take into consideration the probability of success whenever you're doing that along the way. So there are some preferences when we start talking about the mathematical notation of dealing with rational preferences. Not going to go into that. A lot of things that you'll see that it's a lot of the same sort of stuff you see in relational algebra um, or basic logic, frankly. Um, so you basically, uh, generally speaking, you're maximizing a utility, as opposed to later on we'll talk about some of the things that you try to minimize, something like loss or cost. So um, maximum expected utility principle, and this is a good sort of thing because it is something that is mentioned pretty consistently in the literature, is choose the action that maximizes expected utility. Note that an agent can be entirely rational, consistent with the MEU, without ever representing or manipulating utilities and probabilities, lookup table and tic-tac-toe, and so on. Humans, we may not be great at utility. We usually try to be, but so um, sometimes we rationalize more than we actually pick. This isn't necessarily something we care about. So this is a good conversation about utilities mapped to states to real numbers, but what numbers, a standard approach of human utility, which is how good is something or how bad is something, best possible prize with probability of P, or the worst possible catastrophe with U minus, with 1 minus P. So um, yeah, that's $30 is equal to instant death, or 30 $30 with very slim odds of the sudden death. Probably not worth it though, still though. So money is not necessarily it does not have a utility function, but it may have an impact. You can talk about the utility of having money or being in debt, but money into itself is not necessarily the thing, right? And that's true in life. Expected monetary value, a probabilistic formula, um, and people are typically risk adverse. Uh, when people are deep in debt, they are risk prone. So if you're looking to get out, you may make irrational decisions. And this is kind of comparing the difference between a lottery and insurance. Um, so the concept being that basically with insurance, well, a lot of times you're basically paying for the peace of mind, not necessarily the actual insurance itself, although sometimes you don't have a choice. So you'd rather have the $400 in insurance, you'd rather have the lottery, which is probably the case. They would, because it'd be much less chance of a claim in that scenario. So we talk about decision networks. It's ways that we're going to make decisions. Um, and simplistic sort of notation. And you do introduce the concept of chance, similar to belief networks or Bayesian networks, sorry, actions and utility nodes. And you want to, this is, some of these are redundant. Breaking through or walking through an example of maximize expected utility. I'll leave that for you. And decision or outcome trees is another sort of a way of representing decisions and making decisions, similar to a decision tree, but this is more about the outcome. And again, giving you a calculation for determining a maximum expected utility. And a similar sort of approach for calculating utility based upon the outcome trees. Value of information is an interesting characteristic, and it's something that definitely has a temporal component, right? So the basic idea here is that you're going to calculate the value of acquiring evidence. Sometimes you can do it from a decision network, which we just kind of briefly covered. So you may be willing to pay something to be able to go drill some holes to find out if there's some oil. Um, and it may or may not be worth the decision. You don't know till you drill the holes. Um, there's also this concept of perfect information versus something that's not perfect, so probabilistic. Very few things in the real world, though, are going to be perfect. Um, Formulas for calculating the value of information um, in various forms. And some of these are kind of the characteristics of the properties of this information is it's clearly the value of perfect information is always going to be greater than zero. You can't have negative value because well, it really wouldn't make any sense. Um, they're non-additive and they're the order interdependent. So let's go over that. The value of imperfect information, or there's not really such a thing. Information corresponds to observations of a node in the decision network. So it's really not information if it's that imperfect, and there's not really much way of calculating a value to it. And it's representations of how you would potentially do the determination. Sometimes we deal with uncertainty. We don't necessarily know preferences. So they know some things about the world. There's some things that are there that can't really be observed, but they can infer. And they generally create a model that helps them figure out what that is. So that's kind of the point of a model, is you're trying to represent unknown variables in a way so that whenever you can take the things you can observe and determine potentially what those unobservable values are, and using probabilistic reasoning as a way of kind of doing that. So you may use a model of some form to to do a calculation of something that you can't necessarily see, but you kind of know exists. And so that's one approach, and then it does stress the importance of models. Making complex, sometimes there are complex decisions, right, where one decision depends upon another, depends upon another. So there's a series of states, and you have a series of actions that may be taken, and basically it turns into a Markov decision process. And there's generally some form of reward function, um, and a transition function that moves you from state to state. And you start in a start state, and there may be a terminal state, there may not be. So what's Markov about these MDPs, which was the Markov decision processes, right? Markov generally means that given the present state, the future and past are independent. Markov decision processes means action outcomes depend only on the current state. So basically, what you're going to happen next depends upon what you do right now, not necessarily what you did 2 moves back, although you did get to that state through those decisions. A policy it's a deterministic single agent search problem. It's basically the plan. So a policy is what it will do. It's an optimal plan, a sequence of actions from start to finish. Um, but things get in the way, and your information may not be perfect. Um, so you definitely want to, in the Markov decision processes, you want an optimal plan, which is a policy with pi star, um, gives you an action for each state. There's an optimal policy one that maximizes the utility if followed, assuming that obviously everything is known correctly. And an explicit policy defines a reflex agent. So basically, they're able to go through, follow a series of steps and get the ideal result. Examples of um, various optimal policies. And the utility of sequences. So what preference should an agent have over reward sequences? So basically, do you get more now or do you get more later? Um, it's a decision that will be made. You may consider this concept of discounting. So you may want to not necessarily count what you don't have yet. So something that's if you prefer the reward later on to now, or now to later on. So you basically, this concept of values of rewards decay exponentially. So it's going to encourage a more kind of greedy approach to the problem. And discounting, Each time we descend a level, we multiply the discount once, and it's going to lead you to essentially an exponential thing. Um, think of it as a gamma chance of ending the process at every step. So it's handling the case that you might not get through. It may not get that long reward at the end of the game. Um, so if the game lasts forever, do you get infinite rewards? Probably not. Um, if you find yourself on a Mobius, what is that, Mobius curve, you're probably never going to get out, but you're also probably going to stop gaining points, so to speak. So um, most likely, eventually, you will heat or reach a terminal state, even if you introduce one arbitrarily. An example of algorithms for Markov decision processes, taking the concept of racing. You got a robot car, you want to travel far quickly. The car has three states: cool, warm, hot, or overheated. You have two actions, so there's two speed settings: fast or slow. Going fast gets double the reward, but also is going to cause it to overheat sooner. So you might come up with a search tree that helps you figure out what is the optimal way to get there, with the decision points being fast or slow. So if you go fast, 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 you're going to blow up your car, right? So if you go slow, 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 you're not going to get all that good of a reward, but you will get the finish. So the difference, whenever you're dealing with a Markov decision process search tree, you're going to be doing something called an expecting max, like search, instead of min max or something else, and it's around the expectation of the reward along the way, rather than kind of the worst case. Um, again, kind of a wrapping up. Markov decision processes. You have a state of a set of states S, and you have a start state S of 0. Set of actions A. You have some transitions, and you have some rewards, and you potentially have a discount. Um, and you have this concept of policy, the choice of actions that are going to be done, and the utility, the sum of discounted potentially rewards. So solving those, we start off with that same search tree, and then you start figuring out kind of what are the combinations and how much do you get with each one. Um, and it's we're doing way too much work with the expect a max, and some of the states are going to also repeat. So you only need to compute them once, because there are going to be patterns. If you go fast, go slow, go fast, go slow, then that's a pattern that's going to start merging with the same sort of expected utility. Um, So the value of the utility of a given state is the expected value starting in S and acting optimally. The value utility of a Q state is expected utility starting out having taken action from a start state S and thereafter acting optimally. And then there's the optimal policy. And again, policy is the list of actions you take along the way, and you don't deviate from them, and it's deterministic in the sense that you know what they're going to do. Uh, the recursive definition of value. You also have this concept of time limited values, where things may expire over time, or you have so long to do it. Um, and it's kind of similar to a depth K, right, in that sense, because it only goes for so long. And then whenever you're computing time limited values, you would think of it kind of that way. And a way of calculating values through this value iteration, it's an iterative process. We're going to jump to the end. And so eventually those things are going to converge down to a certain value. Bandit problems are something that are used to describe basically associated with one-armed bandits and gambling. A similar sort of concept of giving discounts, or there are no discounts. You have 10 time steps and so on. And it's generally speaking a win or loss sort of proposition. Win has some sort of a value that you get back. You pay so much to play. Um, and I'm going to skip over that. If it's something that's interesting to you, do feel free to dig into it in the text. But getting close to statistical sort of stuff again, so I try to stay away from making this a stats class. The, the final topic we're going to talk about is partially observable Markov decision processes. Um, and basically, while Markov decision processes have states as actions A, transitions P, S prime to given S and A, and so on. With rewards, you add to that observations and observation functions, and they're basically you have then a belief state. So it adds in a certain amount of perception or belief into it. So it's a general solution for map belief functions to actions. So gives you the choice of being able to do something based upon what you believe to be the case, not just explicit values. And so with that, we come to the end of this discussion. Uh, Hopefully you can use something here to get started on your paper uh, uh, related to making decisions. As always, you can do something like tools that help. A good search would be tools that help in decision making processes and tie it in some fashion to something that deals with artificial intelligence. And I will certainly be pretty lenient on the choices and the variations you choose to do. With that, I'll wrap this up. If you have any questions, feel free to let me know. That's what I'm here for. Stay safe, and we'll talk again next week.